Hi, everyone, and welcome to my presentation. As mentioned, my name is Hanif Pourshahbaz. I'm a PhD candidate at university level. Today, I'm going to talk about a question that is can CFD modeling simulate the ice structure interactions in the river? Actually, it's a question of a bigger project, which is my PhD, which is the evaluation of the effectiveness and applicability of ice control structure for flood management. This work is supervised by Dr. Tadris Gobriel from university level and Dr. Ahmed Shakibaninia from Polytechnique Montreal. So first of all, we want to know that why these questions come in our minds. So what is an ice jam? Ice jam is actually a localized accumulation of ice in the river. So what happened? It actually blocked the channel flow. According to the mechanics of the formation, we have the surface ice jam, like here in the CentrEau, Quebec, and we have the phrasal ice jams. Actually, ice thicknesses, river alignment, slopes, and velocity, all of them can contribute in making an ice jam. So as the water level rise quickly compared to the normal floods, is actually the ice jam floods are more dangerous. Any river that can form an ice cover has the potential to have an ice jam. For example, in Canada, in the Athabasca River in Alberta, we have ice jam in April 2020. Or in a Quebec that I live right now, in the Shadow River in April 2019, or in the Saint-On in 2020, we have the ice jam floods. So if we want to reduce the damages of the ice jam floods, according to the Dr. Hicks, we have the structural and the non-structural measures. Structural measures, it means that we're going to build an engineering design, engineering a structure on a river. And we have different types, like the piers or boulders, like the Credit River. We have dam and weirs, like the Israel River, ISIS. We have the weir and piers, like the Sartijan Dam in Quebec, Saint-Georges. We have the ice booms, like in the Saint-On River in the Quebec as well. And we have the other ice control structures, which is not classified in the other categories, like what we have in the, again, Saint-On River in the Quebec. So as we want to evaluate that, are these ice control structures work correctly? We have three approaches. We have the historical study and long-term field observation, like what Lever and Gush did. We have the laboratory experiments, like what Dr. Brian Morse did in university level, or we have the numerical modeling, like Dr. Shakibani Nia's team do in Polytechnique Montreal. About the historical and long field term field observation, we have pros and cons. The pros is that we have the real data, which we can validate our numerical models. But as you know, or if you have done any field observation, you can see that we have the problem with the fields because it's dangerous. We can put one parameter aside. Accessibility is hard, and we have some problems. About the laboratory experiment, we have the very reliable data, but the problem is that, as Dr. Shen says, we have the problem with satisfying the scale effect. So what should we do? We go to the numerical modeling, but we have to, for a good numerical modeling, we have to use the pros of the all things together. So about the numerical modeling, we have the 1D model, like the HECRAS. Most of the engineers right now using the HECRAS, and it's a 1D model and it works. One of the rarest model in the 2D model, we have the crisp 2D, and it gives us more data, like what Nolin did for the river in Quebec. For the 3D methods, we have the meshless or mesh-free methods and the mesh-based method. Actually, it helps us to see the highly dynamic interaction of the ice and the ICS and the vertical velocities near the ICS. So the question is that a meshless or mesh-free method like the DEM-SPH or DEM-MPS or a mesh-based method like the DEM-FVM, finite volume method. Which one should we use for the numerical modeling? The meshless or mesh-free methods, they are flexible, more flexible and accessible, but they are not user-friendly. But on the other hand, the DEM-FM, the mesh-based method, they are user-friendly, but they are the commercial software. They have some limitations. But when you see a video, something like that, it reminds you the sentence that we can use these models to actually simulate an ice jam with the floating granule mat. So the objective of this presentation, and first I'm going to talk about the whole objective of the PhD. In the whole objective of PhD, first I have the field data, which I choose an instrument, some sites, and then I wanted to talk about the capabilities of the numerical methods for simulating the ice structure interaction. And then I wanted to use the numerical method to optimize the design of the ICSS and maybe introduce the new structural measures. So for the river ice processes, so quantifying the river ice processes, I have the field observation 1 and the field observation 2, which is the winter 2022, 2023. This is the winter 2021, 2022. We have them modeling the simple systems, which is we're here assessing the capability of numerical methods and how we're going to connect these together with a calibrated and validated model and the results of the field observation season 2. We're going to use them to model the real life system and then optimize the design and then introduce the new structural measures. Actually, this part of the project by itself is a master project as well. And in today's presentation, I'm just going to talk about this part of the project, which is the modeling simple system. So I'm going to talk about the evaluating a mesh-based method, DEM-FVM, which is actually in the Flu 3D Hydro to do the simulation of ice and ice control structures, and how with the laboratory experiment and other numerical methods. For the methodology, as I said, we have the laboratory experiments. The laboratory experiments actually did in the Polytechnique Montreal by Dr. Ahmad Shakibani team. So in the first laboratory experiment, we have the dam break with the 4 and 9 blocks. 4 and 9 blocks are here, the gate open. These blocks are go to the end of the channel, hit the end of the channel, come back. They have a complex phenomena. Then we add more complex phenomena, which we go to the 25 blocks in here, and we add the piers that each shows us the ice control structures. And then we add more complexity to the problem. So we bring 160 block in a channel and with the ice control structures, which are the piers again. So in each step, we try to use more, to add more complexity to the problem. So for the numerical method, we have DEM-MPS, DEM-SPH, and DEM-FM. The first two, they are fully meshless methods. And the other one is the mesh-based method. The DEM-MPS is developed by the M-Parts, DEM-SPASH is developing by Dual Physics, and DEM-FM is developing by Flu3D in here, Flu3D Hydro. So we have these experiments. We have the dam breaks with the 4 and 9 blocks, 25 blocks with ICS, and 160 block with the ICS. Actually, Dr. Shakibani Niak used this method and they published a paper in 2021 for the 4 and 9 blocks. And then they moved and used the SPH, another meshless method, and used it for the 9 blocks, 25 blocks, and 160 blocks. In my project, I'm using the mesh-based method to have a comparison between the meshless methods and the numerical, between the numerical methods, other numerical results of the numerical methods, and the laboratory experiment in here. So about the results that we get from the mesh-based method. First, we have the dam break with the 4 blocks. We see that we have the acceptable wave profile and block positioning. For example, in T 0.8 second, we have a backward wave that was generated very well. When the gates open, the water hit the end of the channel and it creates a backward wave in here. At the T 1.6 second, we have the reversed wave. So the water hit in here, come back, we have a reversed wave in here that generated correctly. But we see that the mesh-based method in DEM-FM or the Flu3D Hydro model, actually it shows the better block positioning. One of the way to actually see that numerical method works in this scenario is to actually follow the blocks in the different direction. In here, in the X and the Z direction. So we're going to follow the block B2 and B1 in the red and the green one in here. In here, we have the results of the Flu3D. In here, we have the results of the DEM-MPS method. And in here, we have the laboratory experiment. We come and we actually have this diagram. And in diagram, in the X direction for the B1, X direction for the block of the B1, X direction for the B2, and the Z direction for the B2 as well. And here you can see the 3 experiments in the dot simulation, in the dot that is actually graphed in here. And we have the DEM-MPS method, meshless method, and the DEM-FM method, which is a mesh-based method that we actually put them together and look at the movement of the blocks, and we compare them with the results of the laboratory experiments and other numerical methods. Actually, we see that the profiles of the movement, they have the acceptable results, and we see that the water service that generated has a good results as well. So we add more complexity to the problem. So we add 9 blocks. So from the 4 blocks, we came to the 9 blocks. Again, we see that the numerical models and numerical methods, they have the good agreement. So again, the backward wave generated correctly. In the first, we have the laboratory experiment, meshless methods, and in here, the mesh-based method. Then when this wave hit the water, we have the wave collapse. We see that the wave collapse in here in the middle images, it actually generated well. But after the T 1.6 second, we see that the last blocks in the Flu3D actually stuck in the bottom of the channel, which is maybe because of the poor meshing that we used. Again, we followed the movement of the blocks in here, C3 and C2 in the red and green, in the X direction and the Z direction to see that if the model works correctly or not. So in here, as you see, we have the three experiments again. In the dot, we have the one meshless method, which is the DEM-MPS in the red. We have the DEM-SPH in the green, and we have the DEM-FM in the black. Actually, one question that maybe arise is that why the laboratory experiments repeated 3 times and why they have the different datas. Actually, the laboratory experiments uh, did 3 times because it's a very complex phenomena to be sure about the general movement of each blocks. And actually, the results are very close together. So again, for our numerical methods, we want to further step to add the 25 blocks. So right now we did the 4 blocks, then 9 blocks. Right now we're at the 25 blocks with ICS. In here, in the previous slide, we see that we have just a dam break scenario. But right now we have a dam break scenario, but we added the piers in here. So at the top, we see the laboratory experiment, meshless method, and the mesh-based method. Right now with the 25 blocks and the ICS, which here there are the piers. We see that actually we see that the wave that was generated in the numerical methods, they were faster than the laboratory experiments. And we see that some phenomena is not going to be modeled in the numerical methods. For example, in one of the experiment, we see that the one blocks actually flip in here, but in none of the numerical methods we see that. So we see that actually the last row of the blocks in here in the mesh-based method, they actually simulated better. And we see that the reflected wave that was generated, which means that the gate opened, the water go, heat of the channel came back, and again heat of the ICS again. In here we have the reflected wave. We have the reflected wave with the good accuracy. Again, we came to see the movement of in the direction of the X in here for the block of 12 and 16, and in the Z direction for the block 21, 22 to see that if the blocks, the movement of the blocks are okay or not. So we have the laboratory experiment, we have the meshless method and the mesh-based method in the middle, and we see the movement of the blocks and the results of that. About the computational time, which is an important part of the numerical modeling. For the 3 second, we see that the Flu3D hydro for the 4 and 9 blocks, we have about 28 hours with this specification of the CPU because the Flu3D or the DEM-FM method in here are the base of the CPU. With about 1.8 million cells, we have for the 25 blocks, we have the about 60 hours of the time. For the meshless method, with this about 5 million particles, we have between 30 to 60 hours of the time. And the DEM SPH, with the 25 blocks, for the 25 blocks and about 1.8 million particles, it needs about 24 hours computational time. So in total, DEM-FM, which is in here, the DEM-FM method, which is in here, is put in the Flu3D Hydro, show good accuracy and the capability in interaction of water, ice, and a structure. And actually, it's we can compare the results is comparable with the meshless methods. But we have to know that actually it has a very user-friendly interface, but we have to know that the application is limited compared to the meshless methods, which are the open source, and it's more easier to handle. So about the accomplishment and future work, we actually, the part one of the work, we published a paper, the title evaluating a CFD model for three-dimensional simulation of ice structure interaction in the CRIP 2023 conference that you can see on the internet as well. For the future work, actually, we're going to talk more about the numbers that we need. And we talk with more numbers for the comparison. According to the Flu3D manual, the limitation is 500 objects. We're going to use right now I'm modeling the 160 blocks to actually go to face more challenging part and see that how it works. And we're going to actually do some research about the other influential factors like the turbulence model in these simulations to finally do to model a real life system. So in the end, I have to say thank you for the Quebec Ministry Public Safety who support my work, and Flu3D company who gave us academic license for this work. Here are my references, and thank you so much for all of you who listened to my presentation, and thank you for the CentrEau who provide this opportunity for me to have this this presentation. If you have any questions, I'm here and to answer. Thank you so much.